In section 5.1 and 5.2, remember we use Riemann sums to go through and I guess first estimate what the value of the net area or the definite integral of a function was. And then at the end of section 5.2, we did some crazy problems like this. This wasn't the last problem that we did, but we just set this up to say that if I'm looking for the definite integral or the net area of this function between 0 and 10, we had to set this up as an infinite limit of a Riemann sum where we had to sit down and figure out, well, how wide is each rectangle? And then this is the function value evaluated each of the right endpoints. So that's just a very quick refresher of what we did. But if you remember, it took 15, 20 minutes to go through that whole process. And that was for something that was a relatively straightforward function. It's just a polynomial. It wasn't like we were working with cosine or natural log or anything like that. There's got to be a better way, right? This is something that ends up being relatively important for a lot of different applications, especially if we get into physics and even statistics. We don't want to be spending half an hour to go through and find that area of some random function. So that's what section 5.3 is all about here. So we're going to warm up with a little bit of an exploration and deal with a function that's a little bit easier to work with. And then, excuse me, take a look at the pattern that we find and come up with what's actually the fundamental theorem of calculus. Okay, so let's say that we're trying to figure out something like the net area between 2 and 7 of, 3x plus 6. Okay, so in the beginning here, again, we're not going to be using Riemann sums this time. We're going to do some geometry this time around. It's one of the reasons I went ahead and picked something that was a little bit easier to work with. That's just a line. And we're going to try to look at some patterns. Okay, and so the idea of patterning is just you do a problem, and then you do a similar problem with the numbers move just a little bit. So if we wanted to, we could draw this line, look at the area between 2 and 7, calculate it using geometry. We could draw the line again, calculate the distance between two other endpoints and find that net area. But you'll kind of see that the pattern that we would get if we just did it that way is going to be a pattern of numbers, not a pattern of processes. And so what the really smart people, 500 years ago, I guess it probably wasn't that long, but the really smart people, when we were first looking at this, just said, well, wait a second. Instead of having both of these guys be numbers here, let's let the bottom number just kind of be 0 at the beginning, because 0 is nice and easy to work with. And then let's let this number up here actually be a variable. Okay, and so this is a quick aside because we really want the variable that we're concentrating on to be the one that we're comfortable with. So I'm actually going to put the x up here. Okay, and so we're going to say we're looking for that area of this function between 0 and x. Okay, but if I just did that, there's way too many x's going on here. And so just taking a step back, you see there that the x that's here and the x that's part of the dx, that doesn't really matter. This is really just a placeholder for the function. Okay, I could put a q there, an n, a k, a y, a t, but that's just a placeholder so that we know what the function actually is. Okay, so this is also called a dummy variable. I don't want to dwell on that because this is the only time it's going to come up in this class, but a dummy variable is just a variable that's there to show a relationship, but you're not actually plugging any numbers into that variable. That's what's going on here. We're not really plugging any numbers into this variable. This is just telling us, hey, graph that line using that variable. So all we're going to do here so that we can avoid a confusion between having the same variables is just switch this. It doesn't really matter what variable you use, but our textbook does use the variable t in these sorts of situations. So we're just going to make that quick change and realize that we have the exact same function and the exact same differential up there now, just using a different variable. All right, so let's go through and now calculate this. It's going to give us a variable expression since there's a variable up here, but that way we can see a little bit more of what's going on in the background. Right, so if you were to take a look at this using geometry, we would say, again, we're going from 0, which is, of course, right at the origin, to x. And then this is a line. When t is equal to 0 here, you plug in the 0, you get a 6. So the first point on our line is right on the right on the y-axis at 6. And then if I plug in x, well, x is larger than 0 in the way that we've drawn it, so it's going to be a positive number. So we have 3 times x plus 6, whatever that happens to be. We don't know what it is. I'll just draw a picture up here. But that point would be what we get when we evaluate 3 times x plus 6. So there's no way of actually coming up with a number there. That's just the y value is what we get when we plug in the x value. Okay, and so the line would, of course, go further than those 2 points, would go on forever. But if we're just looking at this net area, that means that we're just looking for the area between the x-axis and the line right there. And so here, you can split this up into different shapes if you want to, but you can see that it's going to be a trapezoid. And so this is a reminder from geometry, because this will come up a couple times today. The area of a trapezoid is 1/2 times the height times the sum of the 2 parallel bases. And so in this particular case, the base is the bottom. That distance goes from 0 to x, so that is definitely just x. Okay. And then the 2 parallel bases are just the vertical sides here. Well, the distance from the x-axis to 6, of course, is just 6, so that's one of the 2 bases. And this vertical distance going from 0 to 3x plus 6 gives us the other base, and so it's just the 3x plus 6 here. Okay. And so now, maybe combine like terms real quick. The 2 6's become a 12. Distribute that 1/2 x, and you're going to get 3/2 x squared, excuse me, plus 1/2 x times 12 is going to be the 6x. Okay, so as a standalone part, I don't know that that tells us much right now. Okay, but we're going to do this a couple more times, changing this number around at the 0 here, and kind of see a pattern, what changes, what doesn't change, and then we'll be able to make a little bit of a hypothesis here. So I want to keep track of this. So let's just write what we just did up on the board. We just came up with 3/2 x squared plus 6x. Okay, so now let's see what happens if we do something very similar, but let's just change the number down below. And so the idea here is, by having one of our limits of integration being a variable, we can keep track of changes a little bit more than just working with 2 numbers here and keeping one of them steady. We'll have different numbers, we can see a pattern, but this way we'll be able to see a pattern in x's that are going to be a little bit more useful. So we don't want to change much here. Let's go through. Let me double check the numbers I used here. That's what I thought. So let's just say we change that 0 to a 2. We kept the exact same line. It's just we have a different starting point. Okay, so if we do that, then 2 is over here somewhere, x is over here. And again, we're going to have the same situation where we're drawing a line between the 2 points here, because that is a line. If I evaluate it 2, 3 times 2 is 6, plus 6 is 12. If I evaluated x, just like before, we're going to get a 3x plus 6. And this time we're just looking between the 2 x values and the line. And so that's our area. So once again, we have a trapezoid. This time the smaller height here is 12. The larger height is 3x plus 6. And this distance, it's not just x now, it's the difference between x and 2. So that's going to be an x minus 2. So the area, which again is what we're looking for, the definite integrals with the numbers over here mean the net area under the curve. The area is using the trapezoid formula, 1/2 times x minus 2 times the sum of the 2 bases. So add the 2 bases up, you add the 12 plus 3x plus 6. Okay, so at first glance, that doesn't look anywhere close to what we saw before, but let's just go through and see what's about to happen. The 12 and the 6 would combine to create a 3x plus 18. We are about to have to do a bunch of foiling, so there's different orders that you can do this in. Let's just leave the 1/2 out here for now. X times 3x is 3x squared. Then we're going to have an 18x minus 6x. 18 minus 6 is going to give you a 12x. And then negative 2 times 18 is negative 36. Now distribute that 1/2. And 1/2 of 3 is 3/2. We still have the x squared. 1/2 times 12 is 6x. And 1/2 of 36 is 18. Okay. So, at the beginning, it didn't look anywhere close to the same, but you can see right now that we have a definite similarity here. Okay? In both of these cases, we ended up with a 3/2 x squared plus 6x. In the first example, we didn't have any other extra constant. In this example, we do. Okay? So what it appears, and we're going to check this by doing one last example, what it appears here is that the main component, this x at the top here, is what's giving us the 3x squared plus 6x, no matter what we do with that bottom number. Okay, that bottom number is maybe giving us an extra constant here, but the main essence of this, sorry, the area under the curve of this line is that 3x squared plus 6x. Okay, so we're doing one more example because some of you out there might be saying, well, that's just because you chose an area that was a trapezoid both times. What happens if it's not a trapezoid? Okay, so this is the last example that we're going to be doing of this nature. So let's just do one more time. Throw the lower number into a -3. Other than that, we're going to keep everything else exactly the same. And hopefully I can still squeeze in a drawing. I guess maybe I'll do it over here this time. So this go around, if I put in -3, -3 times 3 is -9 plus 6 is -3. So when I put in x is -3, I get y is -3 down here. Okay. And again, just to stay consistent, let's just assume that x is nice and positive. We didn't have to make it positive, but let's say that x is over here somewhere. And once again, that point, we're going to get by plugging in x, it's going to be a 3x plus 6. And so what we have going on here, we're connecting those lines, and our net area is going to be combining these two triangles. And so remember that that's going to be a negative area and that's going to be a positive area. So we'll have to keep track of that along the way. And we're also going to have to know exactly where it hits the x-axis here so that we can know where the triangles start and stop. So this is just quick solving. This would be when y is equal to 0 is when it hits the x-axis. So when is 3t plus 6 is equal to 0? Well, that'd be equal to 0 when we're at -2. And so that's the x value -2 right there. All right, so this time around, we could just use the area formula a couple of times. Let's start with a larger triangle just to keep things in a nice perspective. So the height here we know is 3x plus 6, and the base is x units plus 2 more, so the base is x plus 2 here. And remember, the area of a triangle, not a trapezoid this time, but the area of a triangle is 1/2 times the base times the height. And then we have to subtract off the area of this triangle. Well, the height here is just 3. The base is 1. So we're looking at 1/2 times the base times the height. Okay. So once again, you have some foiling to do, but we're left with 1/2 times x and 3x is 3x squared. And we're at 6x plus 6x is 12x. 2 and 6 is 12 again. And then over here, that's just going to give you a -3/2. Okay, so I'm running out of room, so I'm going to actually erase this drawing so I can just write the answer up on top here. But look what happens when you distribute the 1/2. 1/2 times 3x squared, it's going to give you the 3/2 x squared. 1/2 of 12 is 6x. 1/2 of the other 12 is another 6. And then we're subtracting 3/2. So, we could put the 6 and the minus 3 halves together, but the moral of the story is we still got that 3 halves x squared plus 6x along with a constant. I guess we can do it real quick. We put that together. 6 minus 3 halves is 4.5 or 9 halves if you want to keep it in fraction form. But we once again have the same basic expression along with a constant, where the constant changes when we change the bottom number. Okay, so now we have to make one pretty big jump. We'll prove this in a second. But at this point, if we can figure out what this expression is going to be just by looking at the original function, now we have a really nice, easy tool to be able to find the actual net area here. So just take a look and compare the function that we started with the expression that we're getting. Ignore the fact that this has a t and this has an x. But if you do a comparison here, this should look really familiar. And we could go both directions, but what's the antiderivative of 3t? Well, the antiderivative would say to keep the 3, increase the exponent by 1, and then multiply by the reciprocal of the exponent. So we'd have the 3 times the 1/2, that's 3 halves x squared. The antiderivative of 6, just tack on the variable, you get a 6x. Okay, vice versa. If you wanted to, you can say, well, if I take the derivative of the area, I'm going to get the original function. If I multiply by 2, decrease the exponent by 1, I'm going to get the 3x or 3t. If I just take off the variable, that's just our rule for that, you get a 6. Okay, so the moral of the story here is that we're going to prove this, but if I just talk through this generically, what we would have is that the area between some constant and x of any function, it doesn't have to be that function specifically, but any function, that is literally going to be the antiderivative of that function evaluated at x along with the constant, remember? Okay, so this is almost the fundamental theorem of calculus that I briefly mentioned earlier, but this is half of it and most of the idea. But that's what we get as kind of a guess. We haven't actually proven that this works. That's just a guess of going through and saying, hey, this is what the area looks like for different scenarios involving a change in our limits of integration. Okay, so let's go ahead and prove this now. Okay, so really, we can write this in two different ways. This is usually how it's written, where we can say that the net area is found by taking the antiderivative. Well, we can take this backwards and say then, well, if I take the derivative of the area function, I wrote this as an antiderivative, but if this is representing an area function, if I take the derivative of this function, I should get the, so when I say function, so I should make more clear here. If I take the derivative of this, right, this is a function itself because there's an x in it. We got that expression earlier when we dealt with this. So maybe I should kind of put an arrow here. These are the same thing, just a different notation. If I take the derivative of the outcome of doing all of this, I should get that original function if this is true, right? That if this is the same thing as the antiderivative of the original function, then the derivative of the result here should be the same thing as the original function. Okay, so let's go ahead and check that. So I'm going to write this out using a little bit of nicer notation along the way, but we just got done saying that that's really thinking of the net area as a function. So we just call this the area function for x is equal to 0 to x of some function dt. Okay, so if we have that be our definition so that we can see that clearly we're working in function format, if we're looking at the derivative of that function is the limit, as there's two different variations. The one we'll use is the one where h is going to 0 of the function evaluated at x plus h minus the function evaluated at x all over h. And so really all I did was use this notation to make sure it's clear that we can think of this as a function and make our derivative definition look normal. Okay, but if I actually go through and put those expressions in, it's going to look a little bit messier, but it's certainly going to be easier to work with. If I evaluated x plus h, that's just saying put the x plus h as the upper limit. We're not touching the actual function itself at all. So remember, these are dummy variables. This is just saying, well, this is the function we're basing it on. X has to be up here in the limit of integration. So if I'm evaluating the area at x plus h, I need the x plus h to be there, not down below. And likewise, if that's just an x, that's just our initial definition. The x goes up there. And then finally, this is something that I did not bring up when we were going over section 5.1 and 5.2 because I maybe should have made a passing mention, but we talked about it before. It's in the textbook. But remember that we do have some rules for definite integrals. Okay, so just taking a look at this, if I'm taking the whole area from 0 to x plus h, and then subtract away the area that's going from 0 to x, the amount of area that we're left with is the area that's between x and x plus h. And so that's actually a rule for definite integrals that we've talked about before, but hopefully intuitively that makes sense. So saving it in, if I go all the way to x plus h and then subtract off the portion that goes to x, what I'm left with is the portion that runs from x to x plus h. Okay, so from here, we just have to do a tiny bit of, I guess, drawing / geometry. We can make sense out of that definite integral. Okay, so I'm just making something up here. There's your graph of, say, f of t. And if I'm looking at, say, the area, well, I gotta be careful here. So that's your axis here. There's your x-axis. So if I'm looking at the area between x and x plus h, I'm looking at this sliver of an area here. And that is kind of crazy shape. But as we've said before, as long as h is super small, which we know it is because h is going to 0, then this starts to look more and more like a rectangle. So I'm not going to try to redraw this as a rectangle, but just imagine this is a rectangle. You can either get a rectangle by using the left endpoint, which would be f of x, or the right endpoint, which would be f of x plus h. Or if you wanted to, you can use the midpoint Riemann sort of idea and say that we're looking at f of x plus half of h. Okay, so the distance between these two is h, so the midpoint should be half that distance plus the x. And so it doesn't actually matter which one of these you use as long as h is small enough to make sense. And then down below the base is just h. Okay, so at this point, what we have is that the area of that rectangle that we're using to approximate is just base times height. So it's base times whichever one of these three heights you want to use. And I'll talk through it in a second to make sure it's absolutely clear, but let's use the f of x plus h. So we're taking h times f of x plus h using a right Riemann sum. I'm mostly picking that because that's what we had done in the previous section. We were using right Riemann sums throughout all of that. Okay, so here, this expression is a really, really good estimate for this net area as long as h is small, which again, it is. So what we have now is that the limit as h goes to 0 of this fraction is the same thing as the limit as the numerator. Again, we're replacing with h times f of x plus h. And from here, you can immediately see that those h's are going to cancel out. We're not dividing by 0 anymore, so we are allowed to plug in h equals 0 to find our limit. So this is the function evaluated at x plus 0, which of course, x plus 0 is just x. Okay, so just taking a quick look, it would not have mattered which one of these expressions we put in. If this was just an f of x, you would just get f of x without having to put the extra 0 in. If you put the 0 in for the x plus 1/2 h, if you put in 0 for h there, you're still going to get the 0 here that turns into an f of x. Okay. So at the end of the day, what we're saying again is we've proved what we just saw in the pattern. That if we set this area function to be the definite integral from 0 to x of some random function here, the derivative is absolutely positively that function. It's just evaluated at x instead of t, because remember, t was a dummy variable. What we really care about is that x value up there. Okay, so excuse me. So that's proving what we had on the board just a few minutes ago, that I'll rewrite up here. That if I take the derivative of the area function, I get the original function. That means working backwards, if I need to calculate the area, I can work through the antiderivative. Okay, so let's write the statement that I had up again a few minutes ago that said that the integral from 0 to x of some function, oh my goodness, I'm so used to writing x's, sorry about that. So that integral of some function from 0 to x is equal to the antiderivative of that function evaluated at x plus some constant. Okay, so the only piece of the puzzle we have left is this constant. And we saw that when we were working with our antiderivatives, that we always have a constant, but if we just have one extra piece of information, we can figure out what that constant's going to have to be. So, excuse me. So first of all, I should have been a little bit careful here. I wrote the 0 because that's what we had been dealing with. But remember, when we go back to those original statements, we didn't have a 0 here. We had some different constant. We'll just call this constant A. But remember that all that changed when I changed that from a 0 to an A, or from a 0 to, I think the first one was a 2, or from the 2 to a -3, the only thing that happened when we changed this constant is that that constant changed. And so we can make that change for free to say, well, hey, the bottom number doesn't matter. It just kind of messes around with the constant. Okay, so that makes it a little bit more useful. We're not just working with a 0 down here. And then we're going to take one last idea from our previous discussions of net area to be able to figure out what C is here. Okay, so here, what happens if you, evaluate where x is equal to A? And so we have the A down below. If I put x equals A up here and go through and find this area, the area between the same number, there's no area between those, right? If I say, what's the area between 1 and 1, there is no area. You cannot have area on a straight line. You have to have two separate numbers for there to be an area in between them. So that has to be 0. Okay, so that's something that we've discussed before. Okay, so all that's saying is if I plug in x is equal to A, I should get 0. So, taking this forward, if I plug x equals A into this and get 0, that means if I plug x equals A onto the right-hand side, I should also get 0. And so this very quickly tells you that the constant that we get has to be the opposite of the antiderivative evaluated at A. Okay, so all we're doing is taking this information and putting it together with what we just wrote out, and that's telling you that the got to be careful, the definite integral from A to x of any function in the world is equal to the antiderivative of that function evaluated at x minus the antiderivative evaluated at A. And I guess two last things to make sure that I say. I know that I said the antiderivative here. Remember that the antiderivatives can have constants, but in this sort of notation, we are meaning for this to be the exact same antiderivative evaluated twice. So, if this antiderivative had a constant, and then we're subtracting away this antiderivative that had a constant here, the constant there, they're going to cancel out. There's no more constants to be worried about here. And so we don't need the plus C anymore because we've taken care of that. And then finally, this is absolutely true, but more often than not, when we're actually finding that area, we don't even care about this being a function. We're just evaluating x at some specific number, just like we did here. We've already used a to figure out what the constant is, so we'll just use b up here for the larger of the two numbers. And this, finally, is the fundamental theorem of calculus. There's a variation of this that we'll talk about at the end of the section. But this is the main thing that you need to know in terms of the fundamental theorem of calculus. And this is hugely, hugely important. And again, we don't really get into too many applications, if at all, in this class of working with the area function here. But it comes up all of the time when you're trying to figure the amount of work in a physics class. You're trying to find areas within statistics and geometry problems. It happens all over the place. And it is super cool that all you have to do to find the area is find the antiderivative. And hopefully at this point, it kind of makes sense that it works the way that it does based on what we talked about. But until that discussion, how in the world did that make any sort of intuitive sense at all? Okay, so let's take a look at using this a handful of times. I don't necessarily need to overdo this, but if we know this information, a lot of the problems that were impossible to do earlier or really hard to do become a lot easier. So I'm going right back to the example that I had on the board at the beginning of the lecture here, the same example we did in the previous lecture using Riemann sums and limits and such. If we use the fundamental theorem of calculus to work through this, what this is saying is that we need to evaluate the antiderivative at 10 and 0. Okay, so we're looking at the antiderivative evaluated at 10 minus the antiderivative evaluated at 0. So all we need to do is find the antiderivative. So in this case, the function, the normal function or original function was x squared minus 4x. The antiderivative, again, our rule here for the power is to increase it by 1 and multiply by the reciprocal. Okay, so we increase it by 1, we have to multiply by the reciprocal, so we get a 1/3 x cubed. In the second one, same thing here. The constant coefficient stays, but then increase the exponent by 1 and multiply by the reciprocal. And putting that together with that last term, half of 4 is 2. Okay. And just to reiterate what I said a little bit ago, we don't actually, when we're dealing with the fundamental theorem of calculus, we don't actually worry about that plus c. We don't care what it is, because if I have the plus c here and then we're subtracting the plus c there, it's just going to cancel out. So don't worry about that part. Okay. And then finally, we're just evaluating. If I put 10 in here, you know what, let's not even worry about showing the arithmetic. You guys can use a calculator, but if I put 10 into this expression, we end up with 10 cubed is 1,000. 1/3 of 1,000 is 1,000 thirds. And then put in 10 here, 10 squared is 100, 2 times 100 is 200, so we get 1,000 thirds minus 200. If I put in a 0, those both turn into a 0, so we're really just subtracting 0 there. And then finally, you just do it. 1,000 thirds minus 200, if you wanted to leave it in fraction form, is going to be 400 thirds. If you want to divide it out, you're going to get 133.3 repeating. Again, it's not going to matter to me which way, but in my math lab, just make sure that you pay attention to what the answer blank is telling you to write in there. And that took, as long as we're comfortable with the antiderivatives, that took all of 30 seconds. And this is the exact same answer, same calculation we did last time. That took, I'm pretty sure it took 15, might have even taken 20 minutes to do. Okay, so that's a huge, powerful tool that we're going to be using. All right, so I guess a little bit of minor detail, but this is really annoying notation to use. You can write it out this way if you want to keep track of it and kind of separate the thoughts in your mind, and I think that's a good idea. But at the same time, once you have a little bit of practice, it's going to be annoying to kind of write this off, write extra notation, scratch work off to the side here. So typically, just to rewrite this, I'm not going to work through the whole problem, but just to rewrite it a little bit differently. What we're going to do is still, if you want to write this off to the side, you can. But we are going to just mentally take the antiderivative of the function that we're working with, put a parenthesis around it. So the antiderivative of x squared is the 1/3 x cubed. I guess since it's already on the board, I'm not going to show the work again, but the antiderivative of negative 4x is negative 2x squared. Okay, so here we're just doing the antiderivative. And then to show that we're going to be evaluating at 10 and 0 and subtract, this is our new notation. And we have a vertical bar with a 0 at the bottom and a 10 at the top. Okay, so that's what I'm trying to show here, is that this notation here tells you to evaluate the expression at 10, then subtract the result when evaluated at 0. So I know this is wordy, maybe I shouldn't have tried to write this out, but all I'm trying to say is that's our shorthand notation for writing f of 10 minus f of 0. So at this point, you would just evaluate at 10, so you'd have 1/3 10 cubed minus 2 times 10 squared. And then you have to subtract away what you get when you evaluate at 0. And I'm writing this out just to make sure it's clear. But of course, this is all just 0, and I miscopied there for a second. This should be a 3. Okay, so that's what that notation means. And again, I don't expect you to write all of this out. Just use a calculator or mentally do the calculations, find the number, subtract the other number, and you're done. But that's just a notation that the text, almost every textbook in the world uses, and we'll start using it here as well. Right, so really, the majority of the problems in section 5.3 then just become an exercise in antiderivatives and how comfortable you feel with the antiderivatives you learned at the end of chapter 4. So do a couple of these. This one a little bit longer than I thought, so maybe I won't do all the examples that I had planned. But let's say we're looking at the net area of the function, the square root function, from 0 to 4. Okay, so first step, realize that we're going to be using the antiderivatives with the fundamental theorem of calculus. To do the antiderivative of the square root function, it's easiest at least to rewrite this as a fractional exponent. And then for our antiderivative, we're supposed to increase the exponent by 1 and then multiply by the reciprocal of what you just wrote. It should have some equal signs here. And then our notation then is that we're taking this expression and we're going to evaluate it at 0 and 4 and do our subtraction. Okay, so here we're going to have 2/3 times 4 raised to the 3/2 power minus 2/3 times 0 raised to the 3/2 power. Okay, not nearly as much to write, but again, the same expression, evaluate at 4, evaluate at 0, and subtract. Okay, and just like before, 0 raised to any power is 0, 2/3 times 0 is still 0, so that just disappears. And use a calculator as necessary, but hopefully you kind of remember some of this. The 2 in the bottom tells you to take a square root, so the square root of 4 is 2. The number in the numerator tells you to take that answer and cube it. So we get 2 cubed there is 8, and 2/3 of 8 is 16/3, which again, depending on what it's asking you to type out, could be 16/3 or could be 5.33333 repeat. Okay, so again, you can maybe imagine one last time what it would be like to create a Riemann sum using the square root function, and then realizing, well, none of the summing formulas that we were using with polynomials applies to something that's working with the square root or an x to the 3/2 power, however you want to look at things, or x to the 1/2 power. So we'd be in a bunch of trouble here. Okay, but the fundamental theorem of calculus, it's not really a big deal. Okay, so that's a square root function. From 0 to 4, you get 5.33 square units under the curve. Okay, so there's all sorts of different things that you can use this with. Let's do a trig function, just because we haven't done too much trig lately. But let's say we're looking at the integral from 0 to pi over 3 of cosine of x over 2 over 8. Okay, So again, we're going to end up taking antiderivatives, but maybe the first thing that you would want to do is remind yourself that, excuse me, constant coefficients are just going to come out from integrals. So dividing by the 8 is the same thing as multiplying by 1/8. So we can take that 1/8, put it on the outside, so that we can just concentrate on that cosine of x over 2. And then our rule for the antiderivative is the antiderivative cosine is sine. We keep the same angle, if you want to call it that. But then remember, we have to counterbalance this. We have to multiply by the reciprocal of whatever coefficient we have going on the inside. So just like up here, divided by 8 gave us a coefficient of 1/8. Divided by 2 gives you a coefficient of 1/2. The reciprocal 1/2 is 2. Okay. So again, this is a little bit trickier, so maybe double check your answer. If we take the derivative here, we should get this. So the derivative sine is cosine of x over 2. The chain rule says multiply by the derivative of x over 2. The derivative of x over 2 is 1/2. 2 times 1/2 would cancel out, and we're good here. But again, talking through it in terms of antiderivatives, it's kind of a two-step process when you're working with coefficients along with your trig functions. The antiderivative cosine becomes sine. You have to multiply it by the reciprocal of whatever coefficient is on your x. And we still, of course, have to evaluate that at 0 and pi over 3. And you'll notice here, it doesn't really matter what these endpoints are. They're just evaluating at the end. But a lot of times you are going to end up with the 0 as one of your endpoints just because of the nature of what's important in an application. Okay. And so finally, we just have to do the evaluation. So we're taking 1/8. Well, no, 1/8 times 2 sine of half of pi over 3. Half of pi over 3 is pi over 6. Minus 1/8 times 2 times sine of half of 0 is 0. Okay. And just always be careful here, because remember that if we're working with cosine, cosine of 0 would not disappear, but sine of 0 does. Sine of 0 is 0, so 2 times 0 is 0, 1/8 times 0, that's all 0 again, so we can just ignore all that. And then over here, again, use your calculator if you absolutely have to, but hopefully you have this memorized. Sine of pi over 6 is one of the special angles that you would learn in trig. Sine of pi over 6 is exactly 1/2. 2 times 1/2 is going to just give you a 1. So the final answer we get here is 1/8, or 0.125 if you prefer a decimal. So I think I'll just stop here with the majority of those type of examples, because it really is a repeat of what you've done previously. I don't want this lecture to drag on indefinitely. It's already, I'm sure, long enough, but that's the idea. And so one last thing that we have to talk about, and this is just something where I didn't want all the technicalities to come out all at once, but the fundamental theorem of calculus doesn't work with every single situation. So we could be working with, say, the integral from -3 to 5 of 1 over x. Okay. And so here, let's take a look at a visualization of why this one will not work with the fundamental theorem of calculus. So if we're looking at our graph, 1 over x has an asymptote at 0, and it does something like this. Right, so obviously over on the other side, I should have been close to the x-axis, but everybody hopefully sees what I mean. And if I'm going from, say, -3 here to 5, and I'm trying to find this area, that is going down to infinity. Or likewise over here, this is going up to infinity. And I have to be careful, because you will learn in calculus too, if you're going that direction, that sometimes that doesn't matter. Sometimes it's such a small sliver here that you can still find the area, but other times you can't. And there's no way for me to talk about when you can or can't right now. Right now, we just have to realize that an area going up to infinity, whether they were both pointing up or both pointing down or one of each, that's just impossible. Let me put quotes around it, because it's not necessarily always impossible, but I will say in this particular case, it is actually impossible. But it's impossible to find area at infinity. Okay, so again, That is not an absolute true statement. That's why I put quotes around it. But for us, we can't do this. We have to have other tools and other ways to analyze a function to be able to figure out whether you can find the area at infinity or not. Okay, so this is going to cause us to alter our fundamental theorem of calculus just a tiny bit, where we need to make sure that this function is continuous. And as long as that function is continuous, there's no way that you'd end up going to infinity at any point. So we'll rewrite that down and then kind of fix this problem just to show that as long as we didn't have that infinity right in the middle here, we wouldn't have a problem. And so this is really just impossible to calculate because of that asymptote that we had earlier. So this is not a sort of problem that will show up in my math lab as a trick question. They won't give you anything like this, but I just wanted to make sure that you are aware. So the full-blown, excuse me, fundamental theorem of calculus has to add on that statement. Okay, so if you have a continuous function on your interval from A to B, then what we said earlier is true. Okay, so I know it's a minor issue, but it's a big enough deal that I wanted to make sure it was kind of emphasized as a separate idea. Okay, so you have to make sure that you're working with a continuous function. Right? So if you're working with something that's not continuous, which I'm not going to stress here, but if you ever ran into, say, a piecewise function where you had a bit of a jump, you can't do it, all the way through both pieces at once, but you can separate it out into multiple pieces and work through it that way. And so if you're curious about that, just drop me a line, drop me an email, and I'll talk through it. But that is, again, a little bit pushing how much we want to concentrate on the details here. So this one was not continuous on that interval. That's why it was a problem. Yeah, but if I gave you the same integral but changed the -3 to a 1, now we're in great shape. Okay, the asymptote's at 0. 0 is not included in the interval that we're integrating over. So this one is doable. And so here we have to take the antiderivative of 1 over x, and be careful. You might be tempted to write this as x to the negative first, and then try to add the exponent multiplied by the reciprocal. But remember, when you do that, when you multiply by the reciprocal, you end up dividing by 0. 1 over x is the one that gives you natural log. And so this is going to be the natural log, technically the absolute value of x, just to open up other possibilities, but it's the natural log of the absolute value of x, evaluated between 5 and 1. So this is going to be the natural log of 5 minus the natural log of 1. The natural log of 1 is actually 0. So you end up with the exact area being the natural log of 5, which ends up as a number being 3.22. That is not right at all. So if you're following along here, I'm going to just cheat. I accidentally miscopied the example that I gave you. So I had an extra 2 in my example that I forgot to write down. So just forget about this. It should be about 1.61. So sorry for that little bit of a detail that I screwed up. So just ignore what I wrote there. Natural log of 5 is about 1.61. Okay, so that's about it in terms of using antiderivatives to find that area. Again, some antiderivatives are trickier to find than others. We will address some additional techniques in section 5.5 to help with some of the harder ideas, but that is the main component of section 5.3. But the other thing that we need to be aware of is that there's a second version of the fundamental theorem of calculus. Oops. And this one I don't like to dwell on as much because it's more of just working backwards in a fact. But if you're told that the area function, just writing that out again, is from a to x of f of t dt, then derivative of a is equal to f of x. And we kind of had that written on the board before. So that's how I would describe it as a teacher. Just to make sure it's clear, we're just taking the derivative of that expression that we got when we went through and did those calculations at the beginning of the lecture. But when you take the derivative, you get the original function back. The textbook will write this out as the derivative of the definite integral with respect to x is equal to f of x. Okay, so that's the way the textbook would write it, and excuse me, we still have that same idea where we have to be working. Well, no, I lied. This works regardless. I was about to say we have to be a little bit careful that the original function is continuous between 0 and x. But even if this wasn't continuous, you'd still be able to say, well, it's not continuous at that point, so this is not going to be continuous. It's just the nature of how the derivative works. We don't have to actually state it out, but in essence, this still needs to be continuous. Okay. So another way of looking at this, that is the actual statement. But when we go to use this, it's actually a little bit easier to throw in one extra step. Okay. So that extra step is just saying, well, forget about taking that derivative initially, and hopefully it made sense because we talked about it before. But the first part of the fundamental theorem of calculus literally told you, I'm sorry, that should have not been a 0. I keep messing things up at the end here. That should have been an a, just like we've been working. It doesn't matter whether that's a 0, a, b, 12, that constant will not matter when you take the derivative. But this, from the first part of the fundamental theorem of calculus, is the antiderivative evaluated at x minus the antiderivative evaluated at a. Okay. And if I do that, now it becomes clear that when I take the derivative of the first function, the derivative of the antiderivative just gives you the original function. And that, even though it looks like an antiderivative, that's just a constant, right? A is the number that we're plugging in. So this is a function evaluated at a number. When you take the derivative of a constant, it just turns into a 0. And so you get f of x that way. And so I'm only showing this step because there are a handful of tricky questions in the textbook. I tried to avoid them in my math lab because it's not a huge deal, but at the same time, I don't have complete control over my math lab. And every once in a while, it randomly creates a problem that I did not intend for it to create. So if you add this extra step in here to help you make sense of this portion of the fundamental theorem of calculus, it really helps, I think. Right. So let's do just 2 examples, and then we're finally done with section 5.3. Okay, so we'll do one relatively straightforward example and then one that's a tiny bit trickier. But let's say that you're asked to find the derivative with respect to x of the integral from -13 to x of e to the x squared minus 3 plus the natural log of x minus, I'm just being ridiculous here, the cube root of x to the 4th plus 1. And I just made a mistake. Again, I'm so used to writing x's that I wrote x's here, but these need to be the dummy variable for this to make sense. You cannot have an x in the limit. You can and have an x down here. So I apologize. These should all be t's. So it should be t squared minus 3 natural log of t and t to the 4th plus 1. Okay, so this is the easy version. Okay, so this is just a fancy f of t. And so once again, you can look at this and say, excuse me, that we're working with the derivative of the antiderivative of f evaluated at x minus the antiderivative of f evaluated at -13. And when you take the derivative, you're going to get f of x here, since that's an actual function. That's just a constant, so it disappears when you take the derivative. I should have canceled it out there. And then finally, all you're doing then is saying, well, there's my function. I just have to replace all the t's with x's, which is the main reason I made the mistake I made earlier. But, excuse me, your end result is e to the x squared minus 3 plus natural log of x minus the cube root of x to the 4th plus 1. And so I realize in this example, I probably wrote too much in the middle. As long as you understand the relationship, the fact that really definite integrals and derivatives are almost opposites, just like antiderivatives and derivatives. You don't need this. You can just look at this and say, well, there's an x there, there's an x there. So when I do this, it cancels out. All I have to do is replace all that expression with an x. But this is kind of the reason why it works. That our fundamental theorem of calculus says that it's the antiderivative evaluated x minus the antiderivative of the constant. You take the derivative, you figure out what's going on here. And so the reason I wanted to show that stuff in the middle is that every once in a while you get a problem, and this is something that could come up. It's not just a mean textbook problem. You might run into something where you're looking at the derivative of the integral from 2 to, say, an x squared minus x of, let's keep this with maybe a cosine of t dt. And the focus here is not necessarily on the function part, it's on what's going on there. Okay. And at first glance, you'd look at that and say, what the heck is going on here? And why do I have a whole expression here instead of just a variable? And again, this is pretty rare, that's why I don't want to draw this out, but it is something, again, that will end up coming up to a degree in calculus 2. So our main concern here is just this. What in the world do I do with that? As long as you write out those in-between steps that I showed you kind of in the definition in that last example, it's really not so bad. You would look at this and say, well, let's just hold off on taking the derivative. And again, we're just going to kind of cheat and call this f of t so that I don't have to use any sort of fancy notation with a cosine. But the first fundamental theorem of calculus tells you that we're taking the antiderivative evaluated at x squared minus x minus the antiderivative evaluated at 2. Okay. And now it doesn't look so scary. It's going to be a little bit annoying to keep track of, but when I go to take the derivative here, it's just the chain rule now. Okay, so we take the derivative of the outer function would give us the inner function. So I said that wrong. The derivative of the antiderivative, right? The derivative of the outer function is going to be f, since that's an antiderivative. The derivative of the antiderivative is f. We still evaluate that at the inner function, but now we have to multiply times the derivative of the inner function. So the derivative there is just 2x minus 1. Okay, so it's the same thing that we've always done. Derivative of the outer function evaluated the inner function times the derivative of the inner function. This is once again a constant, so it turns into a 0 and disappears. And then finally, it's just a matter of evaluating our function that was originally given to us. Okay, so this is going to be cosine of x squared minus x times 2x minus 1. Okay, so again, it's a little bit annoying, but it's the exact same setup. You just get an expression here that forces you to use a chain rule versus just a variable where you could take the derivative naturally. Okay, so I apologize for a couple of mistakes I made along the way there. I guess it's too early in the morning for me. But as always, if you have any concerns about how any of this works, let me know, and I'll try to explain it a little bit more clearly. But I guess the last thing I'll leave you with is that I feel like there's some important details that we needed to talk through along the way here to tie things together to what we've done previously. But as long as you can find the definite integrals using antiderivatives, that's really the main focus of this section. So make sure that you understand the relationship there and how to do that. And let me know if you have any questions as you do your homework.